Hi everyone, and in the beginning of this new year, welcome to the final episode in the series of training videos dedicated to radio signal propagation and antennas. This is our final episode and it will cover the history of the antennas and the main types, the classification of the antennas. And I hope that this final episode is going to be more entertaining and fun for you, with some interesting facts from the history, with some hardware which I'm going to show you today. And I'm glad that you came all the way through the previous episodes, and today will be our summary, and the knowledge that we gained through all of these videos can be used today to comprehend the antenna subject the best way possible. So let me start to ask you a question about this man. This is a very important person in the history of the antennas and of the radio communications in general. And please let me know if you know who I'm talking about. Who is this inventor? Who is this engineer? What is his name? Please write your suggestions in the chat, and I'm going to elaborate more on his inventions and on his work. And I'm going to disclose how is this related to the antennas, to the history of the first antennas, and to the emergence of the first radio communication devices as such. I'm sure that most of you know his name. Maybe nobody knows how this man looked like. That is why it's still silent, and I hope somebody's watching us today. Okay, let me wait for a little bit longer. No options? Really? All right, then the mystery now will be unveiled. His name is Henrik Hertz, and he is famous for trying to prove the Maxwell's theory behind the Maxwell's equations, and to prove the existence of these electromagnetic radiation, electromagnetic waves. And the story goes the following, that between 1886 and 1889 he conducted a series of experiments in his laboratory that would prove the theory summarized by Maxwell, and which later laid out as the Maxwell equations. And in fact, he was the one who proved the existence of this electromagnetic radiation, electromagnetic waves, which were called later Hertzian waves in his honor, because he was the first one who proved them to exist experimentally, in an experimental way. So let me show you his invention a bit later, but for now let me ask you the next question. What do you think was the invention of his own that started the whole antenna series project? And actually you already see the answer on the screen, and it was the dipole antenna. So he used this dipole antenna, and we can say that he invented it unintentionally. He used it as the mean to prove Maxwell's equations, to prove the existence of electromagnetic waves. So his apparatus was made from the transmitting circuit, part, and the receiving part. The transmitting part used this dipole antenna, and the receiving part used loop antenna also. That was the first dipole antenna and the first loop antenna. But the dipole is the most common type of antenna at all, and we consider that this was the first antenna designed for this particular purpose of transmitting and receiving, in this case for transmitting the electromagnetic waves. This is how it looked like, his apparatus, which he used during his experiment. And you can see that it consists of this is a transmitting part, right? So it consisted of capacitance-loaded dipole resonator consisting of a pair of 1 meter copper wires with a 7.5 millimeter spar gap between, and ending in 30 centimeters zinc spheres. So when this induction coil applied a high voltage between the two sides, there were sparks across this gap which created standing waves. And the standing waves, as we learned the previous time, generated electromagnetic waves which had been received by the loop antenna at the receiving side. The frequency of these waves was around 50 megahertz. And this is how the Maxwell concept was proven, and this is how the first electromagnetic radiation was produced using this transmitter and receiver. Okay, let's now get to the second person who is also very important and familiar for most of you, I'm sure. But the question is, do you know how this gentleman looked like? And this is his face, his photograph. So now I'm asking you the second time, who is this gentleman? This is the second most important person in terms of the creation of antennas, of the first antennas. So he is involved in the creation of the antennas as well. Again, this wasn't his main purpose, but for the purpose of another nature, he invented the second type of antenna after Hertzian dipole antenna. I'm sure you know his name, so let me just wait. As a radio engineer, any radio engineer knows his name. Of course, you can guess even. Who could be this person who lived in this end of the 19th century? I'm not sure if he looks like Edison, but good guess. Yes, and the second guess is Marconi, and this guess is correct. His name is Guglielmo Marconi. If Massimiliano is watching us today, maybe he is going to correct my pronunciation. Sorry for that. Sorry for badly pronouncing the Italian names. But he is known as the father of the radio, the first inventor of the radio itself. And he used a second type of antenna for this, for his transmitting and receiving circuits. So, how was this possible? Actually, while developing radio telegraphy, Marconi, who was an Italian inventor and electrical engineer, tried different arrangements and shapes of antenna. But even with improvements, he was able to transmit signals only up to 1/2 mile or less than 1 kilometer. That was not the result he expected, so he played around with different designs of his antenna. And the breakthrough came in the summer of 1895, when he found that much greater range could be achieved. After he raised the height of his antenna and, borrowing from a technique used in wire telegraphy, grounded his transmitter and receiver. So the key point was grounding the transmitter and the receiver. And this improvement allowed him to achieve the distance of 3.5 kilometers and to transmit his signal over the hills, Thus, the first monopole antenna was created, was invented. And as we will learn a bit later, the frequency of the waves for the monopole antenna is reduced comparing to the dipole antenna. So he could use the lower frequency with the same dimensions and transmit further. And this type of antenna radiated vertically polarized signal, which could travel longer distances. Actually, by grounding his antenna, he achieved the minimizing the dimensions of this antenna. So he cut the antenna dimensions in half compared to the dipole antenna. All right, and another interesting thing, getting back to Henrik Hertz experiment. This is a bit fun, which I found about his experiment. And ironically, that Hertz did not realize the practical importance of his radio wave experiments. He stated that, quote, "It's of no use whatsoever. This is just an experiment that proves Maestro Maxwell was right. We just have these mysterious electromagnetic waves that we cannot see with the naked eye, but they are there." And when asked about the applications of his discoveries, Hertz replied, quote, "Nothing, I guess." So that's quite funny. Little he knew about how huge the whole enterprise is going to be in the future, and that he laid down the basics of the radio communication themselves. And some pictures concerning how the invention of Marconi looked like. So this is a drawing from his patent from 1896, showing his first monopole antenna. There was a receiver, transmitter on the left and receiver on the right, on this left picture. And you can see the metal plate, which was suspended and attached to the transmitter and receiver. And you can see it in the picture. There is a wooden bar and there is a metal plate hanging above, connected with a wire and going down to this building where the transmitter was placed. And later he discovered that this metal plate is not necessary, and he can only use this wire which is connected to the transmitter and grounded. The transmitter itself was grounded, and the hanging wire was just suspended on a wooden bar, forming a monopole antenna, actually. So the dimensions of this antenna was not so small, but again, he was able to cut this dimension in half for the same frequency of the waves. And on the right, you can see a picture of how the transmitter itself looked like, with all other elements. Okay, then let me show you how we can classify all the range of antennas. So, initially, Henrik Hertz invented the monopole antenna. Marconi improved the design, we can say, and used the the first was a dipole antenna. Then Marconi improved the design, made some changes, and invented the monopole antenna. And then it started with experimenting and inventing new species of antennas. And now we have dozens of them. So how can we classify them in order to better understand the differences, the similarities, and to compare different parameters and different applications of each? Actually, antennas can be classified in different ways. The first way of classifying the antennas is to separate them between the directional antennas, omnidirectional antennas, and isotropic antennas. This isotropic is grayed out because this is more of a theoretical concept. Actually, it's very difficult, if not impossible to make such an antenna because anyway you will have to attach feeder somewhere, and its radiation pattern won't be equal, won't be isotropic, equally radiating to all the directions. So this is more of a theoretical concept, but still it can exist. So the real world antennas can be divided into directional and omnidirectional. And this is how we classify them by the direction. The other way of classifying them is to divide them into aperture antennas, such as horn and slot antennas, reflector antennas, for example, parabolic or corner reflector, microstrip antennas, such as circular shaped, rectangular shapes, so different shapes of microstrip antennas, the array antennas consisting of multiple elements, like Yagi-Uda and aperture array antennas, and the wire antennas, such as dipole, monopole, or loop antennas, which have been the first types of antennas invented. Also, this can include any other classification. So the subtypes, there are a lot of them. I just mentioned the most common ones. And by dividing them in these categories, we classify them by construction. So how they are constructed, what is the form factor, and what are similarities in their design between different antennas. Also, these two classifications doesn't necessarily exclude each other, right? So they can overlap between each other. For example, there are directional antenna in different categories if we classify by construction. For example, aperture, reflector, microstrip, array could be directional, while dipole, monopole, and loop antennas can be omnidirectional typically. This is the most common way of dividing them into directional and omnidirectional. Of course, there could be some exceptions to this, but I wanted to show you that there are different ways of classifying them, and we can even overlap different classifications between each other. So one antenna can belong to different classes. And another way of classifying them is to divide them into aperture antennas, the antennas which have aperture or an opening kind of a radiating element. It could be just a hole, like a waveguide. It can be a parabolic reflector which has its own aperture. It can be microstrip, just a piece of trace on the PCB or printed circuit board. Any other way also will do. The other type is linear and loop antennas, which are monopole, dipole antennas, and other more exotic antennas. And finally, the array antennas. And array antennas consist of multiple elements, of an array of elements. So they can combine either different aperture elements, or different linear or loop elements together. So we made up the combination of both, and we make up the combination of both to produce this array antennas type. So here are just a few examples: slotted waveguide arrays, phased arrays, patch arrays, etc. And this is how we classify by the source of electromagnetic emission. So the source is either aperture or a line. I mean, it could be just a wire or a rod, and it could be an array of these elements, of multiple elements combined together. Okay, so now I'm going to show you the properties and main characteristics of each of the main types of these antennas. We are going to divide them by the construction in order to distinguish between different design types. And we're going to start with the first antenna ever invented by Henrik Hertz, with the dipole antenna. So what are the dipole antennas? This type of antennas are still one of the most commonly used in the engineering. And here are the visualization of how the electromagnetic field is distributed over this antenna. We can see that the feeding element, the feeder, is connected in the middle of both rods or both wires of both elements, right? And there is a standing wave occurring, like we learned previous time. And there is a electromagnetic wave produced by this alternating current over these two elements, right? And let me show you some practical examples of these antennas. So this is the first one. This is used for 4G, 5G applications. This is dipole antenna inside of this plate, inside of this enclosure. It can be connected with the SMA cable here. So this is one of the examples. This is even more common example of a dipole antenna, and you can see them, for example, on the Wi-Fi routers and hotspots, etc., on this user-grade communication equipment like this. So these are some examples of the dipole antennas. And as a feeder line, we use a balanced line. This is important. The balanced line, what does it mean? The balanced line, okay, let's start with unbalanced line. The example of unbalanced line is a coaxial cable. And it means that this is a line, is a pair of conductors intended to carry electrical signals which have unequal impedances along their length and to ground and other circuits. So the impedances of two conductors are unequal, right? So that makes the line unbalanced. And an example of this is a coaxial cable. An example of a balanced line which have equal impedances of both conductors is a twisted pair. But we can transit from the unbalanced line to the balanced line with a device called balloon. This is not a balloon like you can see to be sold for the kids, for example. This is another type of balloon, and this is just a shortening of the balanced to unbalanced line name into the one word. So this is a combination of two words, balanced, unbalanced, forming balloon. And this is a device which allows to get the balanced line out of unbalanced line. So it can use on the feed of the dipole antenna. Or we can connect the twin wires straight away to the feeder to have the balanced line on the input. There are different subtypes of this dipole antenna. The small dipole, or also called Hertzian dipole, which he probably used in these experiments, is of the dimension has the dimensions of 1/8 of a wavelength, and you can see that the peak directivity is about 2 dBi, and half power beamwidth is quite wide, it's 90 degrees. If we increase the dimensions, and for example we use a half wave dipole which has a length of half wave of this frequency to be transmitted, then half power beamwidth becomes narrower. It is around 78 degrees now, and the directivity improves. And again, if we increase the dimensions even more to the 1 wavelength dipole, then we have half power beamwidth of just 47 degrees, and the directivity again higher, 2.4 dBi. Another subtype of these dipole antennas could be crossed dipoles, which is literally two crossed dipoles, one over another. And this is used for some circle polarization applications, like military, for example, UHF satellite telecommunications, because satellite communications has to use circle polarization. It is not it doesn't have definite direction, so the circular polarization will help us to receive the signal equally from different parts of the sky. And also, as most of the simple antennas, dipole antenna has a subtype of dipole arrays. So this is the compendium of multiple elements, dipole elements combined together. Also, we can call this a standing wave antennas, because this is what occurs while we feed this antenna with a signal. As for the radiation pattern, this is how it looks like. This is how the radiation diagrams look like. Two of them in 2D and one three-dimensional diagram. On the left we can see how it looks like in the elevation plane, and further to the right we can see how it looks from above, so in azimuthal plane or in horizontal plane. And in three-dimensional picture you can see it as a donut, the shape of a donut, which combines these two pictures in the 3 dimensions. And this is the typical application of this antenna. So we can say that this antenna is actually omnidirectional, because it transmits equally in any direction if we look at the azimuth plane. So it is, in this sense, the omnidirectional antenna. It has nulls above and below the radiating element, but the maximum to all the directions in azimuth plane is equal. And this is how we can find different radiation patterns in the elevation plane. So let's imagine this is the side view of the transmitting element. And this is what we get if we change the dimensions of this antenna. Let the frequency be the same for all of these pictures. So we assume this antenna to be used for the constant frequency selected, but we change the dimensions. And we change the dimensions starting from half a wavelength on the very left on this picture. And then we start increasing the dimensions to 3/4 of the wavelengths, for example. And what we see here is the increase in the directivity. So now the directivity increased from 2.15 dB to 2.75 dB. So the half power beamwidth becomes narrower and the directivity increases. Then we go to the whole wavelength dimensions of this antenna, and again we can see the improvement in the directivity and narrowing the half power beamwidth. And further on until we reach 1.5 of a wavelength. Then something interesting happens. The diagram itself changes its shape. So the directivity now is less because the energy is radiated over the multiple lobes, not just 2 main lobes, but kind of a side lobes become more evident, and the direction of these lobes changes. You can see now there are 4 more main lobes in 4 directions. And then this changes continues, this transformation continues until we obtain very exotic radiation patterns of multiple wavelengths dipole antennas. And if we are speaking about the dipole arrays, the most popular is Yagi-Uda antenna. This is actually what you may know as the television antenna, simple one. It looks like this, very often can be seen on the roofs of the buildings and used for the television signal to be transmitted. But this is nothing else but a combination of multiple dipole antennas, which are combined on the same driving element, and each of these dipole antennas, each of these elements has its own purpose, its own role. So there is a driving element where the signal is applied. There is a reflector from which it is reflected, because this is the directional antenna, not omnidirectional antenna like the simple dipole. And there are directors in order to improve this directivity, to send the signal in the desired direction. So we can see the radiation pattern is directed to one single main beam, not like in case of dipole where it is omnidirectional. An interesting fact that maybe some of you wondered about the name, because this is not a usual name. What does it mean at all? Yagi-Uda is quite a funny name, right? And the name goes from the inventor's surnames. The inventors were Japanese. So it was primarily invented by Shintaro Uda from the Tohoku Imperial University, Japan, in 1926, with a lesser role played by Hidetsugu Yagi. So the main inventor was Uda, the man with the surname Uda, and his assistant was Yagi. And ironically, that sometimes in usual conversation, while mentioning these antennas, we forget the second part. So we call them just Yagi antennas. But Yagi was just assistant of the main inventor, and the main inventor's name got lost when used by the radio engineers. That's a shame. And the second historically invented antenna was the monopole antenna, and as we learned, it is just the same dipole antenna with one element absent. So the second part of this antenna is absent. Instead, one of the elements is grounded. And we can see that the second element is actually exists as an image. So it is imaginary element. It is sufficient to connect this element to the ground in order to have an electrical image of the second element. So for the same frequency, the dimensions can be halved, reduced in half. All right, and the radiation pattern looks like as for the dipole antenna, but only in the upper hemisphere. So in the same manner, one part of the radiation pattern is cut, is eliminated, so we only left with the upper hemisphere part, if it is directed upwards. And consequently, the radiated power of the monopole antenna is 2 times smaller than for the dipole antenna, but the directivity is 2 times larger than for the monopole antenna. And also, the gain of the monopole antenna is dependent on the ground plane surface area. If we measure it in wavelength, then we get the graph like this, where it starts, at some point it starts linearly increasing, not linearly, but it starts constantly increasing if we increase the ground plane. And there is a additional subtype of the top-loaded, so-called top-loaded monopole antennas. So here are some examples of them. This is because the low-profile antennas are more compact and aerodynamically preferable. For example, for using in the aviation, on the aircrafts, we want to reduce the size of this monopole antenna, and that is why we use the top loading. So we put an additional element on top, and we make the electrical length larger than the physical length. So this top loading allows us to keep the physical dimensions smaller, but electrically it will conform to this selected frequency and to the selected parameters, and we are not going to sacrifice our performance, right? So we add additional top-loaded element. It could be a loop, it could be just an additional horizontal element, and the electrical length will be the same as for the larger antenna. Actually, we can increase this by a factor of 2, this length. By doing this, consequently we are increasing the gain of this antenna. However, we are sacrificing cross-polar discrimination, or XPD, as you remember from the previous lecture, because we use another element which is perpendicular to the main element, to the main body of the antenna. So this antenna becomes more keen to receive the other polarization, which is perpendicular to the initial one. Initially, it receives mostly vertically polarized signal. By adding the horizontal element on top, it can be more susceptible to receive the horizontally polarized signal as well. And the next type of these antennas is the loop antenna. Schematically, it can look like this. And we can see here actually an example of balloon. There is a coaxial line, and the transition from the coaxial line using a coil from the unbalanced coaxial line to the balanced line connected directly to the feeder of the antenna. So this is an electrical schematic of the balloon, which we learned recently. And as you may notice, that the balanced signal is what we require on the input of this antenna. That is why we're using balloon if connected to the unbalanced line. Quite a broad frequency range for this type of antenna, from 20 MHz to 3 GHz typically, and gain is proportional to the loop that is enclosed by the area. By the area which is enclosed by this loop. There are two main types. One type is a circular, the other is rectangular or square antenna. And with the same conductor length, we have more area enclosed by the circle than by the square. So consequently, we can have more gain using the circular antenna than the square antenna with the same length of the conductor. This can be produced as the printed circuit track, so on a PCB, or just an additional element, a separate design. This is two types of the television antennas, which you maybe know for some older equipment, or used with some radios or television, but not that often in modern days. The next type is a microstrip antennas, and these are antennas which consist of the tracks on printed circuit boards and different shapes over the printed circuit boards. So the feeder line could be multiple. It could be just a microstrip line. It could be a coaxial line with its inner and outer conductors connected to the patch and ground plane. This type of antenna is also called patch antenna. So when I refer to patch, I'm referring to the same antenna. And it can be also driven by the aperture or proximity coupling. It is usually used for the microwaves, for some higher frequencies, And because it is very compact, it is used mostly in the mobile devices like mobile phones, smartphones, etc. And the height of the substrate, so this patch antenna consists of a printed circuit boards, right? The metallic patch on top of a dielectric substrate that sits on the top of a ground plane. And the height of the substrate can be just a small fraction of a wavelength, while the length of this patch can be approximately half a wavelength of the frequency to be transmitted. It produces something that we call the fringing fields, which are the origin, which is the origin of the electromagnetic radiation in this case. And here how the radiation pattern look like in elevation plane and in horizontal plane. The next type of antenna is very well known for the microwave engineering because it is used in 99% of cases, I guess. And this is the antennas which you can see right behind my back. These are some parabolic antennas which we use also for in different form factors, in different sizes. And you can see the microwave radio connected straight to this one of the smallest antennas. The dimensions could be starting from 20 centimeters and up to 3 meters, 4 meters even. So it consists of the reflector itself. That is why it has this name, the reflector antennas. And the feeder, which is the separate element, which can be a horn, or a planar spiral, or a conical log spiral. It could be also dipole or log periodic array. The frequency range is the microwave frequencies most of the time, and it is frequency selective. So each antenna by its design can support only some limited frequency range. So we have a variety of these different reflector antennas, each used for its frequency range, for 18 gigahertz, for 23 gigahertz, for 26 gigahertz, etc. But it is characterized by high gains. Usually it is in the order of 30 decibels and higher, and quite a narrow beam width, which is very beneficial in case of microwave communications. Well, this is another parabolic antenna, very small one. This is for the E-band, for the 80 gigahertz, so you can see these dimensions. It is very small, and with a type of a waveguide feeder here. So the waveguide can be connected here, and a waveguide here serves as the feeder line for this antenna and the feeding element, and the reflector is here just inside this radome, hidden inside. Yeah, and the feed itself, the feeding element is usually placed at the focus of the reflector, and the reflector most of the time is parabolic. There could be different subtypes of this antenna, for example, using a single reflector or double reflector even. This is the schematic of the single reflector antenna with this feeder element in the focus along this central axis. For example, this is how it looks like without a radome, when we can see this driven element, this feeder, some distance away from the reflector at the focus point, at the focal point. And this is how it looks like for the bigger antenna when it is hidden inside the radome. So we don't see actually this feeding element because it is protected with this radome. And this is how the other type of this kind of antennas look like. This is used for some lower frequency ranges, and we can get rid of the solid reflector, and we can substitute it with this grid reflector, because this grid is reflective for the lower frequencies. For the lower frequencies, the wavelength becomes larger, and this grid is able to reflect such a wavelength, as well as the solid reflector could reflect the higher frequency waves. So we just make this antenna lighter, more resistant in windy conditions, under windy conditions to wind load, and we cut the price of this antenna by modifying the design of this antenna and using this grid reflector, but only for the lower frequencies. And some more exotic option is using two reflectors, the parabolic main reflector and the hyperbolic sub-reflector. The question about the reflector of the parabolic antenna. Does antenna makers really make parabolic reflectors, or just spherical as close enough? It might make sense for manufacturer machining reasons. Well, I guess that it's more like close enough. The dimensions are calculated based on the not so difficult, not so complex equations, which are meant to produce the parameters of the antenna to be designed. So we use these equations based on the wavelength and on the desired gain. We can actually find these main parameters shown here. So we can see this virtual aperture area, right? We can see the diameter of this antenna. We can see the distance to the focal point from the center of the reflector. And so this is the pure geometry. We need to make sure that this reflector serves as the surface which makes the wavefront perpendicular or parallel to the propagation directions. As the feeder transmits in a broader angle, and different parts of a wavefront hit and bounce off from the reflector, we need to make sure that these reflections are parallel. So they are then transmitted in parallel along the axis of the reflector for better directivity. So this is the pure geometry, and we can find out with a couple of not so complex equations, geometric equations, just some formulas. How precisely does it correspond to the design, to the production and to the machining part of production? This is another question. I guess this is more a question of the quality and of the imprecision which can be tolerated. So maybe this form cannot be fully geometrically right, correct, and ideal, but it can be that the irregularities are in the smaller than the dimensions of the wave itself, and then it doesn't matter on the overall performance. So I guess that this is more a question of the tolerance of irregularities and of the production quality. But the main parameters can be calculated like this from the geometrical point of view. Yes, and this is how the double reflector antenna could look like. This is for some astronomical applications. The radiation pattern is more or less similar in both planes, in elevation plane and horizontal plane, and you can see that it differs. Of course, the larger antenna, we can see that the diagram on the right is used for the larger antenna, 2 times larger for the same frequency. and it has the narrower beam width, right? So it is more difficult to regulate this antenna, to align this antenna, but it is more directed towards the endpoint or the other side of the link, and it is more beneficial to use it for reduction of unwanted interference between the links. The next type is the horn antenna, and I have a couple of them here. This is the pyramidal type of antenna, so you can see it like this old device for amplification of your voice, and it actually works like this, as we see. But this is the waveguide of some for some lower frequency. You can see it's around 6 maybe gigahertz based on the dimensions, and the feeder can be connected directly here, and the design is very simple. It's just a pyramid which has the specific dimensions for the selected frequency and for the selected gain, and can be geometrically calculated, also using not so complex equations. So this is very rigid and prone to some vibrations, resistant to some vibrations and some external effects. So it can safely used for such applications as for the aircraft radars, for example. And in the past, this type of antenna was very common in using for altimeters, for example, or altitude radars on the aircrafts. And another subtype is this conical antenna, which is used for the spectrum compact, for spectrum analyzer applications. But yeah, it has the same principle, and just the form factor differs, and it also has very simple design with a waveguide connected to the feeder line, and just a cone, metallic cone, nothing special itself. So yes, this type of antennas can be pyramidal, conical, and these two different subtypes can be further divided into other form factors. They are fed usually by the waveguides, which in turn are fed with the coaxial cables using the special adapters. And the typical range is the microwave frequencies, usually above 300 megahertz. So for some radars, it is perfect and is suitable. And also it is most widely used for antenna as the feeding element. For example, for the microwave larger dishes, for the parabolic antennas, these antennas are used as a feeding element. So actually it could be an antenna inside the antenna. So combination of two. The one is used at the primary feeding point, and the reflector antenna is used as the main antenna, which directs the power further. This type of antenna can be characterized by high gain, low voltage standing wave ratio, and quite a wide bandwidth. And as I mentioned, the simple design and rigidity is one of the main advantages of this type of antenna. Here how the radiation pattern look like in both horizontal and elevation plane. And finally we came to the arrays, to the array antenna, or the combination of multiple antennas. We already reviewed one of the most common type of antenna, which is the Yagi-Uda, which is the combination of multiple dipole antennas. And the main principle is the same for all these array antennas. There are multiple elements arranged in a predesigned sequence or some particular order, and it can be ordered in just one particular dimension along the x, y axis, for example, or it can be arranged as the surface, like in two dimensions, along two axes, forming a square of the elements. And we can use very different antenna types as the single element. We can use dipole, monopole, slot antennas, open-ended waveguides, horn antennas, microstrip patches. So actually almost every simple antenna element can be arranged as an array of antennas and used as this subtype. Why do we need to do this at all? Of course, and consequently the frequency range is various depending on these driven elements. So why do we use these arrays? We use them most commonly as the phase shifters in the feed network. We use these phase shifters in the feed network, and these arrays are primarily used to direct the radiated power towards a desired angular sector. So if we need to turn our antenna, we can do it either physically turning it, but this is quite difficult because then we have to rely on some mechanical parts and on controlling these mechanical parts, which is often unreliable. So we can turn this antenna electrically by shifting the phase of the signal fed to each element in such a way that the resulted radiation pattern changes. So we are changing the direction without physically moving the antenna itself. And it can be beneficial for some radar applications, for surveillance, for example. So we use it for steering the antenna and scanning without physically moving it. And how does it work from the physical point of view? This is based on the interference between individual radiation fields of the elements. So we have multiple elements, each has its own radiation field, right? And when we change the phase of the signal at different elements, we create an interference pattern when the multiple radiation patterns of each element overlap and interfere either constructively or destructively with each other. And this is what changes the distribution of maxima and minima in the overall radiation pattern. And this is how we can stir and change the direction of this radiation pattern. Here is one of the examples. This is a very popular place, and it was shown in many pictures and many movies, including Terminator. I guess there was some scenes from this place. Do you know where is it? Obviously it's in USA, but this is called Very Large Array. This is a 25-meter radio telescopes used for radio astronomy. And this is one of the largest sites, largest objects of this type. The other very significant object like this is placed in the UK. It's called Merlin, another one. But this one is called Very Large Array, or VLA. So the frequency range is from 50 gigahertz on the upper part to the 73 megahertz on the lower part. And this is used for radio astronomy applications based on the interferometry. So interferometry is a technique which uses the interference of superimposed waves to extract information. So the advantage of this technique that we can obtain very high resolution images of the night sky. Sorry, not the night sky, of course. This is not the visual telescope, this is the radio telescope. So we just receive the radiation from the different objects in the universe, different galaxies, stars, etc. And by using multiple elements like this, which are separated miles one from each other, kilometers apart, we can obtain the better resolution, analogous to the resolution which we would obtain with the same physical dimensions of a large antenna. But we cannot afford to build the antenna that large, so we use multiple smaller antennas which are combined, which work as a whole and combine the signal from different parts together, and then there is a special algorithm which produces these high-resolution images based on the interference between the different parts. So we obtain the signal from different parts, which is shifted by some known phase. So there is a phase shift between the same signal at different points, and these coherent signals interfere with each other, and we extract the information about this signal from the interfering patterns, from the maxima and minima. And this makes this application more sensitive to the radio signals, and thus we can obtain this higher resolution. Another quite specific type of antenna is a lens antenna. This is rarely used because this is a solid antenna, which you can imagine the glass lens, and the same lens is made of metal, so it's quite heavy and not really practical. But the point is to direct the signal as the optical lens would do, but only with this radio signal. The feeder line could be a horn, a dipole, or any other antenna, and the frequency range is typically the microwave. I have never seen this in the microwave industry at all, in my experience. I don't know if any of you have noticed this type of antenna. I just found some pictures in the internet, but I'm not sure if it's very often used in the microwave world nowadays. And these dielectric lenses, which are forming the body of the antenna, convert the spherical wave from the feed into plane wave exiting the lens. So they are quite bulk and quite heavy and unpractical to use, but there is such a type of antenna. All right, another type of antennas is helical antennas or helixes, which are actually spirals made of a wire and connected to different poles of the feeder line. The feeder line is connected to the center conductor of the cable and the outer conductor, which is connected to the ground plane. So one conductor is connected to this helix, and the other is connected to the ground. And the range is up to 3 GHz typically. This type of antenna has two radiation modes, the normal and the axial mode. So when used as a normal, in the normal mode, this antenna acts similar to a monopole antenna with omnidirectional pattern. And this is how it could look like for some mobile applications. You can see that this is actually spiral, not spiral, but helix antenna, but it is working as the monopole antenna by transmitting vertically polarized signal omnidirectionally. And because it is actually a spiral or a helix, it is inductively loaded monopole. And because of that, it can be electrically larger than the simple monopole. So this is an example of top loading or any kind of loading when we change the form factor of the monopole antenna in order to increase its electrical length and to make it shorter. So it can it allows to make this type of antenna shorter. And by the way, if we, for example, if you are familiar with the Aeronet products, with the Aeronet base, for example, so something similar to this is used there, and it actually acts as a monopole antenna, which produces the omnidirectional radiation pattern. But by its form factor, it can be classified as a helical antenna. And the second mode is the axial mode, when the circumference is near to the wavelength of operation. Then this type of antenna starts acting in axial mode. And it radiates a beam of radio waves with circle polarization along the axis, like it's shown on this picture. And by increasing the number of turns, we can result in narrower beam width, half-power beam width of this antenna. And this final type of antenna is a spiral antenna, which actually is literally a spiral. This type of antenna must be connected to a balanced signal source, to the spiral arms in the center. This is used most of the time as a microwave antenna, and it is quite a broad band, so wide band antenna. It covers very wide range of frequencies actually. So it can cover several octaves, and it can be used efficiently for the surveillance systems, for the monitoring systems when we want to monitor the radio spectrum, when we want to receive the wide range of frequencies for some military purposes, for some spectrum monitoring purposes. So this is the good type of antenna for that purpose, for the surveillance of the radio spectrum in a wide range of selected frequencies. And also it is circularly polarized, so we receive signal from all the directions, and we can effectively monitor what is going on in the air, and for surveillance purposes this is a perfect combination of having a broad band and having a circular polarization. Unfortunately, the low gain is the only disadvantage of this antenna. Before finishing, I would like to draw your attention to the final type of antennas which left on the table. This one looks like a weapon from some sci-fi movie, and this quite interesting type of antenna, I haven't mentioned it, and this is the final question for you. What do you think? What type of antenna is that? There's somewhere it is written on it, so I have to hide it in case you will notice. So what is that? It looks like Yagi-Uda antenna. Is it really Yagi-Uda antenna, or this is some kind of another type? What do you think? What is your guess? While you are thinking, I will show it from different sides. The feeder point here is actually the coaxial cable, coaxial line, and I don't know what happens here in between, maybe nothing special really, and multiple elements. One of the answers is logarithmic antenna. Alright, so that was a bit close, but it's not actually logarithmic, it's log periodic. So the name sounds similar to this, but not really. So this is a log periodic antenna, and we can see that it consists of multiple dipole elements. This antenna is characterized by very wide range. So it is used for supporting a wide range of frequencies, and this particular example is a combination of two Yagi-Uda antennas. So we can perceive it as a combination of two Yagi-Uda antennas, And each of these Yagi-Uda antenna consists of multiple dipole elements. So the Yagi-Uda itself is an array, and the log periodic antenna is an array of the arrays. So we combine dipole elements, and then we combine these combinations together to obtain wider range, supported range of frequencies. They are arranged in the specific order with a phase shift, but still you can see that actually this is two Yagi-Uda antennas combined together. Well, that's it from my side today, and this is the final episode of the whole series. I hope that you enjoyed, and I hope that you learned a lot of new things, and I hope also that it was entertaining for you. If you have any questions left, then this is the last chance to ask them, and you can ask them afterwards in the comments section, and I will answer. And as usually, we will have a quiz today, the final quiz, the 7th quiz. And sometime after the final answers are submitted, I'm going to verify all of them, and I'm going to select the winner for this quiz. And the winner is going to have his prize as promised. But for now, thank you very much for staying with us all these episodes, through all this series, and I wish you a productive and successful new year, start of this year, and thank you very much for your attention. Bye-bye.